Actually, bone strength works the same way. And so, when you think about a bone, what keeps a bone from breaking? So here's call that a break point. And what keeps the bone stuck together there? You can kind of imagine that all along the bone there are these areas that are kind of glued together. It's the cross-sectional area that determines how strong a bone is. And not the volume so much as the cross-sectional area. Because when it breaks, it has to break across an area. And so if very large animals have very big bones, very thick bones. And I don't know if you've ever seen a skeleton of an elephant. Some of the big natural history museums like the Smithsonian, they have these skeletons and they're very thick bones. And because the big animals have to support a great deal of weight. And to do that, they need a larger surface area. But you think about little small animals like little rodents, mice, rats, and birds even. Very small animals have very thin bones. They don't need a strong skeletal structure. And so you think about it this way. Suppose a person grew from 6 feet tall to 60 feet tall, a factor of 10. A 60-foot tall person would have a bone strength that is 100 times that of the 6-foot person, because 10 times taller, the area cross-section of the bones is 10 squared. It's 100 times as much. But the volume or weight is 1,000 times as much, 10 times 10 times 10. And so to support 1,000 times the weight, you only have a skeletal structure designed for 100 times the weight, then you're in trouble. And so, any human that could conceivably be 60 feet tall, in order to survive, would not really look like a human. It would need these enormously big bones and thick legs and so forth. It would need a skeletal structure that can handle that kind of weight. So that's, bone strength is, it's kind of like lung capacity or breathing capacity. It's very similar in that respect. Let's see, how about heat? Now, if you're a warm-blooded animal like we are, we have an internal thermostat in us, keeping us at a constant temperature. All mammals do this, and so do birds. Birds are also warm-blooded. And so but we lose heat. So inside there are physiological processes generating heat inside our body, but the heat escapes through our skin, doesn't it? So the amount of skin exposed to the air determines how much heat you lose. And as you lose more heat, your body has to generate heat to replace it. And metabolism, I think, is tied to this somewhat. So what happens here? Well, very small mammals tend to be very furry, and because they lose a lot of heat in relation to their body weight. And because they have a lot of a lot of skin area covered by fur that compared to the body weight. And so any heat they generate in their body is lost very quickly through their skin for a very small mammal. And that's why the smallest ones, the mice, the rats, and there's one called there's a little shrew that's smaller than a mouse. It has to eat 3 times its own body weight every day to generate the heat energy, because it loses heat too quickly. And so, these little animals have to eat almost constantly. They have to forage for food, and they eat very high energy food. They eat nuts and insects, things with a lot of protein and carbohydrates and energy. If you go to the other end of the spectrum, next time you see an elephant, look at his fur coat. Elephants, being mammals, have hair, but they have a little hair that stick up here and one there and one there. Almost no hair whatsoever. And so most of those big mammals are close to hairless. They don't have much fur at all, and they love to. They like water. They like being in water to cool off. And the elephant has to have these big ears, and the ears aren't for hearing; they're for cooling, because these big ears there's a lot of blood that circulates through those ears, and so it acts sort of like a car radiator. All that blood circulates through the ears, and it gets exposed to the air and helps cool the elephant off. So if you cut the ears off an elephant, it's going to be in big trouble. It might even die, it might overheat, because it just would lose its capacity for getting rid of its internal heat. So what's going on? A larger animal has an increase of weight according to volume, third power. And so the volume dictates how much heat energy must be produced. Okay, but the ability to lose heat is according to the square, second power. And because heat is lost across skin area. So, you know, the ability to retain or lose heat is just like the lung capacity or bone strength. You know, it's a matter of area versus volume again. And so large mammals tend to run hot, and they need ways to cool themselves off. Small mammals have the opposite problem. They have to stay warm. And now, humans, I've known people who've undergone a very quick weight gain or very quick weight loss. People who gain weight very quickly tend to be very warm. And people who lose weight very quickly tend to be rather cold. Now, I think the bodies adjust, but that in time. But initially, that rapid change in weight is going to impact the ability of the skin to radiate heat, and so you have these kind of predictable results. If you lose say 40 pounds in a month, you're going to probably be walking around with a sweater on. Or something heavier, depending on the temperature outside. But anyway, that also is tied to dimensionality. So all this stuff is driven by dimensionality, and it helps dictate how large animals get, or their physiological structure, and that sort of thing there. Let me see. Now, the ability to overcome gravity is much harder for a big mammal. I mean, you don't see elephants climbing trees, do you? And an elephant would have some trouble climbing any kind of steep hill. Small mammals, like a squirrel. You ever watch a squirrel? It'll skid along the ground, and come to a tree and just go right up it. Okay, you know, gravity doesn't seem to bother little mammals much at all. And what's going on there? Well, it may be related to the body's ability to process energy very quickly. And for example, oxygen, the small mammals can process oxygen much faster, because there's that difference between the area required for lung capacity and the volume required for oxygen. In a small mammal, oxygen comes much easier, and so I believe that may increase the potential power of the muscles. And so small mammals are very, very strong for their weight, and big mammals tend to be rather weak for their weight. And I think part of this is our ability to, the ability to use oxygen. And there may be more complicated things at play here. I'm not a biologist and no authority on this, so there's a little bit of speculation involved here. But I think that has a lot to do with it. Small animals can run very fast for their size, and then you get down to the insect world, and like a flea can jump 100 times its height. If we could do that, we could jump about a mile high. Think of the energy required to move us a mile in one leap, one jump, and it's unfathomable. It's unimaginable. Okay, unfathomable. Can't seem to get that word out.